so first thing I have to do is make a note. I'm just learning how to use this pen, so a lot of times when I make X's, if I draw them too fast, they look strange. So if you see that symbol, it's not a weird caveman drawing, okay? It's just an X, so don't panic about it. Alright, so when we talk about derivatives, okay, we already know our regular, say, x squared. We know the derivative of that. If we were going to take y prime, that would be 2 times x. We know the power rule. Alright, but we don't know too much about trig functions. We noticed the other day using our calculator that we might have an idea of what some of them look like. Alright, but here's 2, the sine and the cosine, and I want to just make a mention here, another note. Anything that starts with cosine, cosecant, cotangent, inverse cosine, inverse cotangent, inverse cosecant, any of them, when you take the derivative, okay, so remember this is our verb, when you take the derivative, it's going to always be negative when we have a co in the front with our trig functions. Alright, so we have these two here. We have our sine, derivative of sine is cosine. Memorize it forever. Okay, the derivative of cosine is negative sine. Again, we have that co, so we have a negative for our derivative. Alright, so let's actually go ahead and try to work on some of these now. We're going to find the derivatives of the following functions. 2 times sine of x. Well, we already know our constant rule. Because there's a 2 there, we're just going to bring it right along, right? So y prime, or dy dx, is going to be equal to 2 times the derivative of sine. And we know that the derivative of sine is cosine. So y prime, or dy dx, either one, is going to be 2 times cosine x. Okay, on our second one here, we have sine of x divided by 2. We can also think of that as 1/2 times the sine of x. So we have f prime of x this time, okay, using that notation, bring that constant right along, and the derivative of sine of x is cosine, again. So our derivative of sine of x over 2 is 1/2 times cosine x. Alright, and for the last one here, we're just combining two different functions. It's our sum of two derivatives. The derivative of x is just 1. The derivative of cosine, we now know that forever, is negative sine of x. So in this case, f prime of x, don't mind this notation, just learning how to use this pen, is 1 minus sine of x. Alright, so now let's try to apply these here. We're trying to find the slope. As soon as you see slope, always think derivative. Okay? Find the slope of the graph of f of x equals sine of x at the origin and at x equals 4/3 pi. So when we talk about slope, we think derivative. So the derivative, because we now have this memorized, the derivative of sine of x is cosine of x. Okay, so if we want to find the slope of the graph, we now just need to plug in the points that we want. The slope of the graph at 0 is simply going to be cosine of 0. Cosine of 0, okay, if you want a quick little drawing, cosine is our x value. That point is 1, 0. Cosine of 0 is 1. So the slope of our graph at 0 is 1. Okay, now if we do part B, we're trying to find the slope of our function at 4/3 pi. So again, we're just plugging it in. Okay, 4 pi over 3. So we're doing f prime of that. We're doing cosine of 4/3 pi. Alright, so you should know these by now. If you don't, Okay, my little shortcut here, 40, 30, 45, 60, starts with a 3. So we have square root of 3 over 2, square root of 2 over 2, and 1 over 2. Alright, cosine, 4/3 pi, where is that? Alright, this would be 1 pi, or 3/3, so it's going to be over here, with a reference angle of pi over 3. Alright, pi over 3 is our 60-degree angle. So cosine is 1/2. So all students take calculus. Only tangent is positive here. So this is, the slope is negative 1/2. Now if we were going to do a bonus problem with these two examples here, I might ask you to find the equation of the tangent line. Alright, if I was going to do that, the only thing you need for an equation is a slope, which we already have right there, and a point. So how do we find the point at the origin? Well, we plug it back into our original function. So f of 0, if we plug in, what's sine of 0? Okay, and sine of 0 is just 0. Use our point, 0, 0, and our slope, 1, and write an equation. Y minus 0 equals our slope times x minus our x value, 0. Alright, and then if I wanted to do it again for this function now, I have to find a new point, sine. If I plug in sine now of 4/3 pi, that should be negative square root of 3 over 2. No, it's a negative. So now our equation of a tangent line here is y minus our y value, which is negative square root of 3 over 2, or plus square root of 3 over 2, equals our slope, negative 1/2, times x minus, and our x value we were looking at there is 4/3 pi. Alright, let's keep going. When we talk about derivative, and we've already mentioned this, remember the slope of the secant line gives us our average rate of change. So the slope of our secant line, that's the average rate of change. Anytime you see average, think secant line. You're using two different points. When we talk about tangent, that's our instantaneous rate of change. So we've been able to do that already, and now we're going to apply it in a situation. We had talked about before a position function, say distance, okay? That is the derivative, or velocity is the derivative of our position function. Let me just erase that here. So position, remember velocity is just the derivative of that. Let me get my pen back. Okay, velocity is the derivative of position. Okay, or the rate of change of position, so it's a distance over a time. Okay, change in distance, another word for that is displacement. Okay, how far the distance has changed. So that's just another vocabulary word that we should mention. Alright, change in distance is called displacement over time. Alright, so instantaneous velocity, we're talking about a derivative rate at that point. Alright. I'm sure a lot of you would love to do this. A calculus textbook is dropped, not thrown, remember, just dropped, from a height of 100 feet. Its height s in feet at time t seconds is given by this function here. This is our position function. So find the following. The average velocity over each of those. Okay, average velocity, we would just have to do s of 2, okay, our y value, the distance at 2, minus s of 1, all over the change in the time. So we have our displacement, how far the position has changed over time. Alright, so I'm going to try to save you some time here. If you go into your calculator, and I'm going to erase it when I'm done, so you got to get it right now. In your calculator, if you don't want to keep going to your table or evaluating this, what you can type in, you could type y1 of, and then put your value, 2 minus y1 of 1 over 2 minus 1. Oops. Okay, y1 of, sorry, over 2 minus 1. You can use that if you put your y1, your function into the y1. So anytime you have a problem where you're going to be using the function really often, so see we have to have a whole bunch of these values, then you want to put your function into y1. Okay, so type negative 16. You could use t or x, it doesn't matter. Alright, so put that into your y1 in your calculator. And then on your home screen, just type y1 parenthesis 2 parenthesis minus y1 of 1. Alright, and then when you do that, I think in this case, we get negative 48, and we always want to put our units here, feet per second, because we were talking about time, feet per second. Okay, so it's negative. That means that we are going down. The height is going down as we move along. All right. If you continue to do the other examples there, let me clear that up. Okay, you continue to do those. You should get the values that I will put up here. All right, this one, part B, you end up with negative 40 feet per second, and you're doing the same thing. Just find the average velocity. We're using the secant line. Just use the slope. Okay, if we check part C, this time you get negative 33.6 feet per second. Okay, and if I continue here, the last one, the average velocity should be about negative 32.16 feet per second. Okay, so as we get closer and closer here to 1, it looks like it's approaching a certain number here. It looks like as we get closer and closer to 1, the slope of the secant line is approaching negative 32. Okay, that's what we're guessing. If we actually perform the instantaneous velocity, as soon as you see instantaneous, you think derivative. Alright, so we take, oops, come on, the derivative of our position function. Now that we know how to do that with the power rule. Okay, 2 times negative 16 gives us negative 32. Subtract 1 from the power, t. The derivative of any constant is just 0. So if we want to find the instantaneous velocity there, we just have to plug in 1. Right, and doing that, you get negative 32 feet per second. Okay, so we were right as our numbers here, they approach negative 32, and that's exactly what the instantaneous velocity, that's how fast the book is dropping at t equals 1 second. Okay, and then we have one more question to go along with this. How fast is the book traveling when it hits the ground? Well, the first thing we need to figure out is when does it hit the ground? Alright, so that would be when our height is 0. Alright, so if we could figure out when our height is 0, then we'll know when it hits the ground. So set our position function equal to 0 here, negative 16t squared plus 100. Alright, so we get 16t squared equals 100. Divide both sides by 16. We can reduce that, and we're going to leave it in fractions because we're not afraid of fractions. Okay. Which would be 25 over 4. Okay, we're going to take the square root here. Always remember plus or minus. So t equals plus or minus 5. Square root of 25 is 5 over 2. Now time, we're not looking at negative time. We start our stopwatch at 0, right? So the time at which the book hits the ground is 5/2 or 2.5 seconds. That doesn't answer the question though. How fast is the book traveling? So now we have to take it and plug that into our instantaneous velocity here. Our velocity is the derivative of position. So plug it in. So we have v of, grab a pen again, okay. V of 2.5. So we get negative 32 times 2.5. Alright, so we get negative 80 feet per second. So that's how fast this was traveling when it hits the ground. Alright, we have one more problem here. So we need to figure out where this is differentiable. Okay, before we can determine if it's differentiable, we need it to be continuous first. Okay, and so we have to remember how to do that. So we're talking about the limit as x approaches 1 from the left side. That's of 3 minus x equals 2. Okay, and let's do limit as x approaches 1 from the right. Ax squared plus bx. You plug in 1 for x everywhere, you get a plus b. Now we know if we want it to be continuous, then they have to be equal. So 2 equals a plus b. Okay, so that we don't know what a or b is yet. However, we'll be able to figure it out pretty soon. Alright, so if we're going to take now, let's look about it being differentiable at that point. We can just take the derivative of each of those parts. So we have f prime of x. Okay. The derivative of this would just be negative 1. Okay. On that side. The derivative of this, use the power rule again. 2 times a, that's our constant, 2a. And subtract 1 from the power, we get x. And plus b. Alright, so in order for this to be differentiable, the slopes both have to be the same. Okay, so if we take the limit of our f prime function from both sides, okay, if we look at the left side, the slope's negative 1. If we look on the right side, okay, we're plugging it into this part now, f prime of x. We get 2a plus b. So now we can combine it with this over here. 2a plus b. Okay, you could solve this. You could set up a system of equations and solve it. Or you can solve for one variable and solve it. Okay, so we have a. We could maybe solve this one for a. Alright, 2 minus b equals a. Now just plug that in anywhere you see a. Negative 1 equals 2 times 2 minus b plus b. Use the distributive property. Oh, that's a negative 1 there. 4 minus 2b plus b. Negative 5 equals b. So b, negative 5 equals negative b, so b equals 5. There's one value. Now we just have to go back and plug that in. 2 minus 5 is negative 3. So there are our two values. Alright. Get to some problems and come in with questions tomorrow.